Welcome back, Nature in Code. We have arrived in Chapter 5. Chapter 5 is all about spatial models. And this is going to be a fun chapter in terms of the visuals we're going to develop in this chapter. So spatial models are models that take spatial considerations into account. And so far, we haven't done this. Most of the models we've looked at so far looked at a very simple world of diploid individuals that at a specific locus in the genome had two versions of the gene, two alleles, either A1 or A2, and individuals would produce infinitely many gametes, so A1 or A2 copies of the allele, and they would produce infinitely many copies of those, so we would have an infinitely sized gamete pool. And then we would draw from this pool, we would draw these alleles, and we would randomly create new individuals, new diploid individuals, by drawing many, many of these alleles. Now, early on in the course, we looked at a world where we assumed the population size to be infinite, and this was the Hardy-Weinberg model. And then we relaxed that assumption, and we assumed that we would have a finite population size, and we saw that the consequence of that is genetic drift, which introduced quite a bit of evolutionary dynamics. However, we still sampled randomly here from this gamete pool, which essentially meant that mating was random. Now, in reality, this is quite often not true. In reality, it's often a case that if you look at the world and you look at a specific individual in this world, and you then look with what other individuals that particular individuals will be mating and producing offspring, you find that there are some spatial constraints in the sense that matings between individuals who are nearby are much more likely than matings with individuals who are very far away. And for most species, that has a very simple reason, and that is dispersal. You can only travel so far as an individual of a species in your lifetime. And this point, I think, is best brought home perhaps if you think about plants. Plants, of course, don't travel. Their pollen do travel, but dispersal is very limited, and the same is true with animals. Think of perhaps a mouse somewhere in your backyard or in a forest nearby. What other mice is that particular mouse going to mate with? Well, it's likely that it's going to be mice in the local area and not hundreds or thousands of miles away. And so we can simulate this process by essentially modeling space explicitly. And so what we could do is we could, for example, assume a world that looks like this. So sort of have a two-dimensional space here. And then we could put individuals on this, on this space. And we could put them at specific locations, and maybe they could move around. And then we could come up with rules like, well, this individual is more likely to mate with this individual and less likely to mate with this individual because they're too far away, something like that. We could certainly do that. It would be a bit complicated here because we would have specific X and Y coordinates for each individual, and then we would have to calculate the distance between all these individuals and then calculate the probabilities and so on. There's an easier way to do this. A more simplified version of this model looks like this. Quite often when people implement spatial models, they implement this grid world. So you have a grid here, and on this grid, you have an individual, like for example this one, occupying a cell. And the simplifying assumption is usually that each cell will contain one individual, and I'm just highlighting here this particular individual. And now we have a much clearer understanding of the neighborhood. So we could say, well, this here is the neighborhood, at distance 1. And now we could come up with a rule, for example, well, individuals at distance 1 are more likely to mate with each other than individuals at distance 2, and more likely than individuals at distance 3, and so on. Or we can come up with an even simpler version where we say, well, we're going to define a mating distance, say d, and this mating distance, if I set it to 1, then this will include all the individuals here in this space, with respect to this focal individual here. And now the individual can only mate with the individuals here in this area. Only within, the area that is defined by this mating distance. So if we went ahead and changed that value and said, what happens if we set the mating distance to 2? Well, then it would simply be this space here. Okay. And now all these individuals here would be, possible mating partners. And we could just select, for example, a random partner out of these individuals here. And so on. And what you can also do in this case, and that's actually quite neat, is you can in principle assume that your mating distance, d, is going to be so large that it essentially encapsulates the entire space here. And that is actually quite a nice property, because if you set the mating distance as large as that, then mating is effectively going to be random again. And now you essentially have a non-spatial model. Even though you're explicitly modeling space, you're setting this value to such a high value, this variable to such a high value, that space doesn't matter anymore. And this is actually quite nice, because now you can compare, very localized versions of your models, so where space plays a huge role, against a version of the same model where space doesn't play any role, by just modifying the value of one parameter. And this is really handy. Now, what about the borders of this world? Well, we can come up with a simple rule that says, okay, if you exit the world here, say, then you simply re-enter it immediately over here. Same down here. If you exit down here, you immediately re-enter up here. And so now this world is essentially borderless. And so when you, for example, try to look at, let's pick an individual maybe here. What is that individual's mating range? Well, it's simply this grid here. And then it essentially continues over here. Okay. So this would be now the mating area of this particular individual. Or you could, for example, assume that you have an individual here at the corner. So let's pick this individual here. So what does this individual's mating neighborhood look like with a mating distance of 1? Well, it would simply be this corner here, and then up here it would be this part, and then over here it would be this part, and then finally over here it would be this part. So even extreme border cases like this one will be quite simple to solve. So there are essentially no borders anymore. Okay, so let's go ahead and implement this. Now, a fair bit of warning. You will write quite a bit of code in this chapter. However, two things. Number one, of course, I'm going to develop this code with you, and I'll guide you along the way. And the second thing to remember is that you now actually have all the tools that you need to develop something like this. As you can perhaps guess from this image, we're going to make heavy use of two-dimensional arrays, and you know about that. And then we're going to use loops, and we're going to use functions and logical conditions, and so on. Things you've already mastered in the previous chapters. And the other thing is, as I said in the beginning, this is actually quite a rewarding chapter because the visuals are going to be real fun. So if you look here at the cover of the book, this visual is essentially a screenshot of the spatial simulation that we're going to develop here in this chapter. All right, so buckle up and let's get started.